Well, welcome everybody. Good morning, good afternoon, wherever you are on the time zones. And it's a great pleasure for me to present as a kind of an introduction, mycotoxin exposure in dairy cows. We talk about animal health, we talk about welfare, and we will talk a little bit about food safety. Now, this is in a series of seminars we were giving, and we are touching in early days, we're touching all animal species. If we go to molds and mycotoxins in dairy cattle, we have to consider that the TMR, so the mixed ration of cattle, in principle consists of two elements. One is the concentrates, and the other part is the roughage, very often on-farm produced roughage and silage products. And if we have to make an assessment of animal exposure, we have clearly discriminate between these two batches of feed that go into a TMR. And in the concentrates, we will focus on what I call the AFOZET panel. I will explain that in a minute. That are the major mycotoxins. Where we go to the roughage, then we do see that we have a number of minor toxins that are not regulated as yet, but can have a great impact on animal health. Now, when we talk about risk assessment of mycotoxins in dairy cows, we have, of course, to start with the very obvious differences. Mycotoxins are mainly described in monogastric animals like poultry, like pigs, but also now with increasing prevalence in the diets of pet animals. And in the same category, you would have to place a pre-ruminant calf. And on the other hand, you do have, of course, a full ruminating animal. And in the ruminating animal, the rumen is also the first site of contact. When we were talking about poultry, we said, okay, the intestinal barrier is a vulnerable structure, and the intestinal absorption determines the internal dose. When we go to ruminants, there is a rumen prior to the intestines, and the rumen microbiota are a very vulnerable structure, and I will explain that later on in this presentation. And the degradation capacity of the rumen determines largely the effect in the animal. So, are the active mycotoxin reaching the circulation, reaching the intestines, the circulation, the liver, or are they already degraded? Or on the other hand, what is the impact of mycotoxins on the functionality of the rumen? Now, rumen stability is the first part we have to address. And rumen stability and the relevance for this is clearly when you go, and I do not see, can you see my mouse? No. Rumen stability determines in principle the internal dose. We have to discuss the major rumen metabolites. And these are, of course, responsible for animal health effects and also from what we can see finally at the outcome, at the disease or the toxicity of these metabolites that are absorbed or the parent compound. Now here you see what I always use as the AFOZET panel, that is the main mycotoxins like aflatoxins, fumigatus, ochratoxin, zearalenone, ergot alkaloids, and the tripotecins. And the tripotecins we normally focus on DON and T2 toxin as the most representative mycotoxins. When we look into the rumen stability, then we see that aflatoxin is moderately stable and stigmatocystin is highly stable. Aflatoxin will be converted into aflatoxicol, and this is a very often neglected metabolite because it's non-fluorescent, and you have to detect it by UV light. So it is a totally different analytical method that we use on a routine base. In terms of toxicity, that means a minor decrease, and of course you all know that both aflatoxin as well as stigmatocystin, the cotoxin with a very similar structure to aflatoxin, hepatotoxic, and also have a so-called IMO effect. And IMO, you find it on the bottom of the slides, stands for immunomodulation, pro-inflammatory response, and cellular oxidative stress. If I go to the other toxins, you see fumigatus is very stable, absolutely unchanged in the rumen compartment, but it has a very, very poor bioavailability. And later on, it can at very, very high concentrations cause kidney damage, which is unusual but typical for cattle that fumigatus causes kidney damage. But we see it very seldom in practice because it requires very, very high concentration. Ochratoxin A. An important toxin in poultry and also in pigs, particularly because in pigs are the most sensitive species, are not of large relevance for ruminant species due to the fact that the rumen can degrade it perfectly to ochratoxin alpha. It's a major decrease in toxicity, and that's why you see that for ruminants, this is a non-regulated toxin, while it is regulated for all other animal species. Zearalenone is modified by the rumen and partly converted to alpha-zel, which is alpha-zearalenol, the hydroxy metabolite, and this is much more potent. Alpha-zel can be 60 times more potent than the parent compound zearalenone, but it has a poor bioavailability. But again, it is in toxification step. So rumen metabolism changes into a more toxic metabolite, and the impairment of fertility is, of course, the major endpoint we are interested in the dairy industry. Ergot alkaloids are rather stable. We see a minor decrease between 10 and 15%. They are not quantified because ergot alkaloids is a group. We measure normally 11 different derivatives, and they pass unchanged in terms of metabolism and efficacy. We will discuss later on one of the ergot alkaloids, not from clavicid species, but from grass and grass-based silages in terms of fescue food. The trichoticin DON, very, very prominent mycotoxins in monogastric animal species. They are largely detoxified with some problems if you have extremely high concentration, because the detoxification capacity, turning DON into DOM, the metabolite which has no epoxide group anymore and has a decreased toxicity, can be limited if rumen function is not very good or impaired by other mycotoxins. Now, if we again go now, what I mentioned before, to regulatory or guidance levels we do have, then you see here simply an overview. It is a mixture of the guidance levels of the EU and those handled in America and in many other countries, the FDA guidance levels. And you see here in principle the same reflection of what I presented before, that the toxicity determines also the guidance levels. And you see for fumonisin in cattle we have a permissible level of 50 ppm, which is very, very high, because normally we count in ppb the concentrations of mycotoxins in feed material. And you see ochratoxin A not regulated because it was degraded in the rumen. Zearalenone very low concentrations permitted or recommended because it is activated. So we can repeat the entire discussion with this slide as well. The special attention should go to the aflatoxin, because aflatoxin has a very, very low permissible level or recommended level. And this is more or less related both to animal health, to the liver toxicity of aflatoxin, but also to the fact that aflatoxin is excreted into milk in the form of its metabolite aflatoxin M1. And aflatoxin M1 is heavily regulated because it's still carcinogenic. So if we go into carry over into milk, and again that all fits together with what I had explained before, we have a carryover of aflatoxins, which is now absolutely changing. And I will explain that in the next slide. In early days, aflatoxins were transmitted into milk in a percentage of 1 to 2%, and this has changed dramatically. You see also the statutory limits on the right-hand side, and these the most right column, and we have the difference between EU levels and the FDA levels, which is quite significant for the daily export of dairy products, because the limits are different. Now you see for all other mycotoxins, the carry over into milk is very, very limited. And that means that we have no regulations on milk and dairy products for mycotoxins other than aflatoxin M1. Now this is a slide I would like to explain you. It's very, very technical, because food safety concerns in relation to aflatoxin M1 have now been changed. And this is a major subject when you talk in daily practice to dairy farmers and milk control systems, so the quality systems of the dairy industry. Because in early days, and that's on the left-hand side, you see that we calculated carryover rates of 1 to 2%. And carryover here means the concentration in feed of aflatoxins, total aflatoxins, particularly aflatoxin B1, and the final result, what is excreted into milk. So it was 1 to 2%. And this is an all standard reviews and was considered as a very, very good guidance level. But genetics have changed. And what you see here is the so-called YY change, which is a minor change in the genome of bovine species, excuse me, particularly Hereford cattle. And this increases milk production. So animals have been selected for this trait because it gives a very, very high milk production. But at the same time, it increases the transfer of aflatoxin B1 and aflatoxin M1 excretion in milk to a very higher percentage we have seen before. So 1 to 2% change now into 8.6% up to 10% if you go into daily practice. This is related to something you see at the bottom of this slide. It's the so-called BCRP, which is a transporter in the mammary gland of the cow, and this transporter pumps aflatoxin M1 directly into the milk. Now you know that the public health concern is the infant, the small baby drinking in relation to its body weight a lot of milk. And at the same time, we know that all carcinogenic compounds or potentially carcinogenic compound, and M1 falls into this category, are much more toxic to the human population when ingested at the early stage of life. And this is why the subject is very much of concern at the moment for the dairy industry, and the controls in aflatoxin M1 contamination of milk have been increased drastically to avoid human exposure. And I give on the bottom of the slide, I refer to 2 review papers we recently published, one already in 2018 on this BCRP, and one very recently with a number of people where we go back into the metabolism of aflatoxin M1 in dairy cows and the consequences thereof. So aflatoxin B1 is excreted in concentrations that are of public health concern as aflatoxin M1 into milk, and these concentrations are so low that they do not cause really adverse effects in cattle, but is a food safety subject. Now with this, I want to close a little bit the first part, the so-called AFOZET panel, and I will go to other components of the TMR, the roughage, or other compounds the animals consume routinely throughout the year, pasture grass, silage, straw, and everything. And here we have a totally different group of mycotoxins and molds we have to consider. And this starts with the endophytes in grassland and with the so-called storage molds we find in silage, like Penicillium bisoclamus monascus and Aspergillus fumigatus. We have in principle more than 80 fungal species that we can identify in silage and in haylage, so preserved feed material, and the origin of these is soil. They are in principle entering at the harvest stage when the material that is harvested is contaminated with soil. These fungal species can enter the silage and then can propagate within the silage during storage. And this I will explain a little bit in the detail, but before I start, I have to go back to the endophytes. You know, endophytes are invisible, the invisible fungi, because they live within the plant, so you not see them from the outside. They even can convey heat resistance and insect resistance to the plant, so they are beneficial for the plant. But when ingested by animals, they will cause diseases, particularly due to ergot alkaloids. The most prominent one is pesky food in the United States, very, very prominent disease in large parts of the western grassland. And this gives these lesions at the foot of the animal and conveys also heat intolerance due to the peripheral vasoconstriction. Now, these have been studied very much at the University in Kentucky, and this slide I simply borrowed from their website, and you see that they already start to discuss the multiple metabolic effects mycotoxins can have on energy intake, feed efficiency, and other effects. And this is the first example, and I will go further without explaining this in detail. I will go further because it is in principle what we see with all these silage molds. If we go to mold and mycotoxins in silage, we see that cows seem to recognize them. And this I use also when I go to farmers and say, look at your cows, because they want to give you a message. And the message here of these two ladies is, this is not tasty. And when you look into the TMR, you find the little mold balls, and on the right-hand side, you saw the enlargement. This is moldy material. This is Penicillium roquefortii. These can be Bisoclamus, that can be Aspergillus. With your naked eye, you cannot discriminate it, but you can find these balls. They look a little bit like an oily substance that is given in the feed. So they are visible, not the fungal species, but the fungal contamination can be visible by these balls. And they have a very, very bad taste for animals, because all these molds produce what we call VOX, the volatile organic substances. And this is what you're all familiar with. That is the moldy substances we also have when we have moldy bread or when we have other moldy food materials. Now, what can we find in silage? And I will go back here to 2 slides because they are representative for many, many publications in the international literature, where silage has been examined for these typical molds. And the most typical molds here are pathogen, mycophenolic acid, cyclopyrazonic acid, and roquefortin C. And roquefortin C, of course, has given the name after the Penicillium roquefortii group as one of the major fungal species producing these type of toxins. Toxin concentrations in silage increase with duration of storage. And what we can analyze, you can see here on the left-hand side, grass silage and maize silage on the right-hand side, is that we have high concentrations of pathogen in particular in grass silage and of roquefortin particularly in maize silage. So this is a little bit different on the material that is used, but you see always that they have a kind of the same pattern of these 4 mycotoxins that we can find. And this is why research more or less concentrated on these occurrence patterns, and we looked into the clinical syndrome of these Moulds and Mycotoxins in silage as an adverse effect on animal health and animal welfare. And you see here again a kind of a summary of clinical pictures of dairy cattle. You see that on the left-hand side, on the top, you see that you can control your silage for aerobic stability with a camera that measures temperature differences, and you see what we all know, the heated area here given in red. And you see on the bottom, you see the cows, with minor lesions on the left-hand side. These animals have problems to stand up. They have mild neurological problems. You see in the middle that they have problems to digest and in the ruminating process. And you see inflammatory response at the legs on the right-hand side at unusual places like the inner part of the hind leg. You see also one of the major biomarkers we use, that is GSH-PX, that is principally a measure for the antioxidant capacity. Now again, what we see is that these molds that are producers of these toxins and of these moldy silage syndrome belong to the groups of Aspergillus fumigatus. I will touch that in a few minutes in more detail, particularly Penicillium roquefortii and Bisoclamus. And as mentioned before, we can identify in principle more than 60 fungal species, and they are all soil-borne. So the contamination takes place during harvest. When we go into these moldy silage and we look again into the animal, then we have to discuss what is a major toxicity. At very high concentrations, roquefortins can even have neurotoxicity. But what we see at the low concentrations, and you see here the insert, which is of one of our papers we recently published, this is the antimicrobial activity. And the antimicrobial activity is very, very high for all these toxins. So what happens is that we give a kind of an antibiotic substance into the rumen every day with every meal. And this, of course, causes rumen dysbacteriosis. And this is a typical feature and typical characteristics of roquefortin C, pathogen, mycophenolic acid, and particularly pathogen is has been a very, very prominent antibiotic. It has been even tested for use as a therapeutic agent, but it has too many side effects for parental application. So it has been withdrawn in the early stage of research, but it is still one of the most potent antibiotics we do know that is naturally occurring. but also fusarium toxic, like fusarium acid, enanthines, ergot alkaloids. They all have antimicrobial activity contributing to rumen dysbacteriosis. If you then go to the animals and look into cow signals related to rumen dysbacteriosis, you can compare this easily with SARA, with subacute rumen acidosis. And you see all the symptoms, you see, we know in principle from the dairy healthcare related to SARA. We see that we have a poor feed intake, a poor feed utilization, a low body condition scores. We have laminitis as a non-specific inflammatory response. We have a decline in milk production that's, of course, of very large economic importance. And we have poor fertility. And this is all related to these mixtures of mycotoxins we can find in silage. And when you go to the details of it, you can see here there's also a slide and a scheme we published quite a while ago, where we try to understand the metabolic pathways resulting from an inflammatory response on the bottom right, the so-called, what I always call IMO effect, so inflammation, immunomodulation, and related to oxidative stress. And on the other side, you have the metabolic imbalance, characterized here by the liver. The fatty acid metabolism is modified. Glucose metabolism is modified. So you can go to all these little details to understand what I mean with a metabolic syndrome. What is invisible, but I mentioned already before, is the secondary form of effects that we never see on the clinical setting. But this is the immune modulation. It is also an immune cell depletion. It can have a systemic inflammatory response. That's what we see with increased cell counts, and that's what we see in clinical practice with increasing prevalence of laminitis. And what we also have to consider that moldy silage contains, in comparison to a good quality silage, higher levels of LPS. And LPS is the endotoxin of gram-negative bacteria, and also from some fungal antigens that again contribute to the overall inflammatory response within the animal. And these basic inflammatory response driven by macrophages results in an increased susceptibility of the animals both to viral and bacterial diseases, and can also be found as is indirect sign in a poor response to vaccination program. So the impact on overall animal health and welfare is much more than just clinical intoxications, but of course we have to consider that the silage is given very often for a long period because it's on-farm produced, and silage, haylage, straw material contaminated is of course given for months to the animal, and then you see this disease complex progressing over time. What I also have to mention that fungal activity in silage as a post-harvest stage, but also in straw and other materials, haylage and so on, the fungal activity represent a kind of a fermentation process. And this fermentation process makes plant proteins available for contaminating bacteria. Bacteria normally cannot use very well plant proteins, but now they are pre-digested, fermented, and then you see a very easy, undesirable bacterial overgrowth. And this has been demonstrated both for Listeria, but also, and more important, for Clostridium species. And Clostridium species like Clostridium perfringens, Clostridium difficile contribute to the overall clinical signs. Even Clostridium botulinum can be found in some silage bales. Also to the group of Clostridium are two species that need to be mentioned here, and this is Butyricum and Tyrobutyricum. Both are very, very detrimental when they contaminate milk because they give an off taste, a bad taste of milk. And in the processing side of dairy products, these Clostridium species that are less toxic for the animal but detrimental for milk production are also controlled now in dairy quality programs due to the fact that they can have a very negative effect on fresh milk products. Finally, I have to mention also Aspergillus fumigatus, because it's an opportunistic pathogen which we see now in different parts of the world increasing. Again, it's a soil-borne microorganism, normally occurring in heavily fertilized soils, and also in terms of the efforts we do at the moment to have a closed circle to save energy and input on the farm, we see that Aspergillus fumigatus is increasing. Aspergillus fumigatus is a facultative pathogen. It has been associated with hemorrhagic bowel disease in cattle, which we all know from the literature, which is a necrotic and hemorrhages in the intestine. But if it's given at lower concentrations or lower fungal counts during a longer period, you see a really wasting syndrome. You see here on the right-hand side, you see one of the heifers you will not recognize because she has no body conditions during condition scores. She looks at if she has been starving, and she has really a problem. We had to euthanize that animal, of course. What Aflatoxin fumigatus is also doing in cows is mycotic abortion, because it can enter the vaginal space and via the vaginal area also the reproductive organs. And we have a mycotic mastitis with very, very high cell counts in some cases that cannot be cured. The toxin or Aspergillus fumigatus is producing toxins, and we call it a so-called toxico-infection. Because fungal mycelium, when once entering the cow, can produce within the cow, in the intestines, in the lung, in the udder, they can produce gliotoxin. And this is one of the few examples we do have. We have it also for some Fusarium species causing eye diseases, but this is the main example of a toxico-infection where both the invasive fungal mycelium in the animal body as well as the mycotoxins contribute to the syndrome. That is also an important disease in human beings, and this is why we have very, very nice theories and also evidence how Aspergillus fumigatus acts within the animal. There's a number of tricks to escape the immune system, because the conidia have a kind of a shield that they cannot be recognized on the left-hand side by immune cells like macrophages, and they have a special killing mechanisms which we called, this is directed to neutrophilic cells and thereby immunosuppression. In the animal's body, the mycotoxins performed are particularly gliotoxins and fumagillin, and these toxins have not been seen in silage as such, but only within the animal body, within milk, but we can also measure them in the digesta and in some cases in blood if the concentration is high. These fungal species are also a concern, as I mentioned now several times, for the dairy industry, because fungal species can also be a hygienic problem. And you see here again, what fungal species can be found in milk. It's not a totally closed system or poor hygiene in the milk parlor. And you see on the right-hand side, you see Aspergillus fumigatus again, and the concentrations of Aspergillus fumigatus spores that can be measured in excreted milk, so in principle also in the milk used for human consumption, is rather high and also related to the somatic cell counts, indicating that here is a subclinical infection of the udder, which can reduce milk production very significantly and particularly results in rather high cell counts. And you know that high cell counts are always related to low milk production. I'm nearly at the end of my story, and I would like to finalize with a number of take-home messages. We have to consider mycotoxins in cattle because they are ruminants. The entire risk assessment is different because the rumen plays such an important role in terms of degrading capacity, inactivating mycotoxins, but at the same time also being a vulnerable structure. So we start in cattle with TMR, and TMR is concentrate and roughages. We look into the rumen microbiota as a first target site in the animal for foodborne mycotoxins, and we see that the rumen microorganisms are very, very active in degrading some mycotoxins, like opportunistic A, but that this degradation capacity is not complete. Fumonisin, ergot alkaloids stay, and the detoxification capacity can be also impaired if you have these other mycotoxins, so these mixed exposure levels, that affect rumen microbiome, then they will also not degrade so successfully the mycotoxins we said they are occurring frequently, like DON. And DON is normally degraded to DOM, to the detoxified metabolite. But if the rumen capacity is impaired, for example, by penicillium toxins, this detoxification process will be slowed down and will be limited. And this poses another animal health risk. The GMR contains these antimicrobial active substances, resulting finally in the clinical syndrome of rumen acidosis, metabolic disturbances, and an inflammatory syndrome. Clinical signs of mycotoxins here are decreased milk yield, increased somatic cell counts, a higher prevalence of laminitis, and a poor reductive activity. What we also see is that we have a secondary contamination with bacterial pathogens like Clostridia, Listeria, but particularly Clostridia are important. And these secondary contamination contributes to the clinical signs we do see in the animal, but also to a poor milk hygiene. And food safety concerns are mainly rising from aflatoxin M1 in milk, and I explained to you that recent genetic selection has increased the risk, so control mechanisms have been increased to avoid any kind of contaminated milk reaching the infant and infant products. The final take-home message I want to give is that mold and mycotoxins are really a One Health issue. You know that we have, of course, mycotoxin exposure of the human population due to mycotoxins in nuts, in wines, in spices, in other kind of plant products. And these exposure levels are can be very high depending on the diet and selection of the material you are using for human diet. But what we have to understand is that global climate change at the moment favors fungal invasion, and thus we will see an increase in mycotoxin contamination of feed materials throughout the world. And this is one you also can measure when you see the big overviews that are published every year. Mycotoxin management practice requires an integrated approach, starting in the first prevention step with crop management at the pre-harvest stage, harvest conditions, preservation of material during storage, and mitigation strategy. And this will be explained in some more detail with the next presentation.